So we've finally gotten to a point in the course where we can begin to speak about calculus. And this particular section, Chapter P, Section P1, is a preview of calculus. What I want to discuss right now are the kinds of problems we can do without calculus, the ones we've already been doing in pre-calculus and algebra and trigonometry and so forth, and the ones that we're going to need some new form of math to be able to determine. Calculus itself is the mathematics of change. It's the mathematics of change. So there has to be some change, there has to be some motion, there has to be a curve. It's not the mathematics of anything static like one xy coordinate. And I know that a curve certainly is something that's changing. But without calculus, we can determine the slope of a line. All we need are 2 points, and we can determine the slope of a line. But how do you determine the slope of a curve that's not a line? Turns out the slope of a curve is the same as the slope of a tangent line. And a tangent line literally is the line that touches the curve at one point, just like that, but it balances up. So how do you determine the slope of a line when you're only given 1 point? And to do that, we need some new form of mathematics to help us with that. So pre-calculus also deals with velocities, accelerations, things like that. But in calculus, we're going to be determining the slope of a tangent line, for example. We're going to be also computing the area beneath curves, like functions. Right now, if I asked you to compute the area of a triangle, the area of a rectangle, the area of a square, you wouldn't have really any problem with that. You'd use the geometric formula for those particular items. But if I said, draw this curve f of x, and then get the area beneath that curve up against the x-axis, now that's a whole different matter. We don't really have a geometrical formula for that particular function. So we do need a different kind of mathematics to determine how to do that. I'd like you to take a look at some of the problems that we can work out without any new form of mathematics. And if you take a look on the left column here, here's a few things we can do. Over in the right, without calculus. We can determine the value of f of x at any given point. That's right here. F of x at x equals c is the f of c, and it's a y value. Don't really need calculus for that. You can determine the slope of a line, but when you're given 2 points, given a point here and given a point here, and the slope is rise over run. You can determine the slope of a line that is secant to a curve, and a secant line is a line which intersects the curve at least at 2 points. So it intersects at this point, it intersects the curve at that point, and because it intersects at 2 points, both of those points can be determined using the function, and then again, rise over run on those 2 points gets you the slope of a line. Another thing you can do without calculus, you can get the average rate of change or average speed. If this were your car traveling from, let's say, Troy to Boston, t equals a would be the time of departure, t equals b would be the time of arrival, and let's say that was departing Troy at noon, arriving in Boston at 3 o'clock. The difference would be 3 hours. Now the distance of this trip, let's say, is 200 miles, and so the average speed on your trip would be 200 divided by 3, which is 66 2/3 miles per hour. So getting an average speed doesn't require any advanced mathematics. You just simply divide distance over time. Curvature of a circle, we all really know the shape of a circle, whether large or small. They all pretty much look the same. They're just scaled differently. Height of a curve when x equals c, well, of course, that's just the f of c right there. That's the y value height. Now let's go down over here and take a closer look at problems where we would need some assistance. We'd need something new. This one we're not quite ready for yet, but basically if your function does not become defined at a particular x value, you can't just put x equals c into the function and expect to get that y value out. So we need something new. It's called a limit, and we'll get into that in the subsequent chapters. But basically, you could compute items on the left side, you can compute items, but you can't compute right here where the curve is undefined. So we need some mathematics that help us determine exactly where that should be. Visually, I can see where it should be. It would line up with the y-axis over here, but we need some additional tools to be able to get that value more precisely. These two are about the same thing. The slope of a curve can be measured by drawing a tangent line. A tangent line touches the curve right there at that one little spot where that's the point of tangency. And it balances up. In a sense, you're going to get an equal amount of space over here as you do over here. And the same for this tangent line here, about an equal amount of space here as you do here. The problem ends up being, how do you find the slope of that line? You're only given 1 point. So this is a real problem. The only way I know how to compute slope is to take the difference of the y values, that's the rise, divide by the difference of the x values, that's the run. Rise over run is slope. Well, I've only got really 1 point. And that's the only point you're really going to be able to determine exactly with the function, because that's the only point that's on the curve. So maybe you can use that 1 point as the 2 points. That's a possibility. So rise over run, use this point as 2 points. They just happen to be the same point. Well, the problem with that is the rise on the same point is 0, divided by the run on the same point is 0. There's no rise, there's no run. They're the same point. And you get this crazy fraction, 0 divided by 0. And that's completely undefined, and yet your eyes tell you that the slope of this line really does exist. So we must need something more to be able to determine the slope of that line. There's another speed called the instantaneous rate of change, or instantaneous speed. Again, along that trip to Boston, maybe your average speed is 66 2/3 miles per hour, but what is your speed at mile marker 85? Maybe it's 80 miles per hour, maybe it's 60 miles per hour. So there must be a means of determining the actual speed at any given input value t or x. Any input or independent value, you should be able to determine the speed. Right now, all we can determine is one number, average speed for the whole trip. The curvature of a curve rather than just a circle, you can see this curve has different curvature than a circular curvature. Another thing you can do is you can take an interval on a curve from A to B and ask for the maximum y value within that interval. Now, you would think you could do that right now with the tools of pre-calculus, but the answer is you cannot. All you can do is go from A to B and just keep evaluating the function. Maybe watch that value go up, 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 and then all of a sudden the value starts coming down, and then narrow your focus on that particular zone and maybe find it that way. With the tools of calculus that we will learn, you'll be able to actually nail that point and say it's exactly at x equals c, and the f of c is the y value at that maximum height. So those are the different tools that we're going to look at. Now, there are other problems that we can do with and without calculus. Let me take a look at a few of these. These are a little bit different. They deal with things like area. So area of a rectangle, area of a square, area of a triangle, these are all things you can compute using a geometric formula. A work done by a constant force, force equals ma, so work equals force over distance. You're able to really compute that pretty readily. Center of a rectangle, just the average x and y. The length of a line segment, that's the distance formula, and some other three-dimensional stuff that you can do right now. But what if I asked you for the area beneath a curve? Where's the geometric formula for this little shape? We don't have one. So you might come up with some ideas, and one idea might be to chop this into a rectangle and a triangle and get the areas of both of those shapes. That would only be an estimate. It would not be the exact area. Work done by a variable force. The centroid of a region, we don't really do much of that, but that also requires some advanced mathematics. And the length of an arc, that's like having a string that connects between these 2 points, and getting the arc length. That's something that you just can't use the distance formula. The distance will give you the shortest distance between the 2 points, and this string is a little bit longer than that. So those are a few other things that we're going to need some form of advanced tools to be able to work with. The first problem I would like to work on, the most fundamental problem in calculus, is the tangent line problem. I want to discuss what a tangent line actually is. Let's discuss the tangent line problem. Now, What's so difficult about it? You're given a curve, and the curve could look something like this. And you're given a point of tangency, maybe right here, and we'll call this point, or at least the x value, we'll call this x equals c. Now, you don't need any advanced mathematics to get your y value, which is simply the f of c. But here's where the difficulty lies. I would like you to take a straight edge and balance it perfectly right on that little point so that there's basically an equal amount of space on either side, and we refer to this as the tangent line. There it is. And the slope of this line, we'll say, is the m of the tangent line. And this is one of the most elusive slopes that we have when it comes to lines because I'm only giving you that one singular point. You normally need 2 points to get the slope of a line. So I'm going to cheat. I'm going to give you 2 points. Now, this is our function. So our function says, hey, if you know an x value, I can get you a y value. So let's get another point. How about over here? Right there. Let's get that point. Now, I'm going to say that this point is delta x away from this point in the x direction. We use delta x to represent change. So delta means change. Delta x, that's how far away it is from that point. So think about how you would label this x coordinate here, right here. You would say that, well, I started at x equals c, and then you went and added delta x. So that's a good representation of my x location. Let's go over here and see if we could pick up the y value. I'd have to shoot over to the y-axis to get it, but you know how functions work. Functions, they very simply say, where are you currently in x? And they really just wrap themselves around that particular input. It's not a very pretty looking input, but that's what it is. C plus delta x goes right there. So if I were to connect these 2 points with a line, let me do that, and let's discuss it. Now, the first thing you probably notice is it's not the slope of the tangent line. It's incorrect. However, we have a name for this kind of line. When you connect 2 points that exist on the same curve, we call that a secant line. So this is m secant. Now, again, I'm having a hard time getting this tangent slope, but I can compute the secant slope. The reason I can, because I've got 2 points. So slope is rise over run, which is the difference of the y values on top, the difference of the x values on the bottom. And let's see, the top y value is represented by f of c plus delta x. The bottom y value is represented by the f of c. This x value is c plus delta x. And this x value is just c. So it turns out that the slope of the secant line can be represented like this. So the reality is, yes, you can compute the slope of the secant line. The other reality is, it's not what I'm really looking for. I'm looking for the slope of the tangent line. But it's close. In fact, I think we can make it even closer. What if I decided to make delta x a little smaller? Instead of that big, I'm going to pull delta x in right over here, let's say. This will be my new delta x. So in fact, you can kind of think of delta x as shrinking. Maybe this is delta x1, and this will be delta x2. You notice I'm shrinking delta x a little bit here. Okay? So you get yourself a new point by shrinking delta x. You get yourself a new secant line. This was secant, we'll call secant 1. And now look at these 2 points. So let's connect the dots with a line. And take a look at what just happened. Now this line also has a slope, and I'll call it m secant 2, but I like that slope a whole lot more. Let's zoom in and take a closer look at this. What happened was, by making delta x smaller, the slope of my secant line is trying to approach the slope of the tangent line. In fact, probably the smaller I make delta x, the smaller I make it, the closer the secant line is to the tangent line, the closer the secant slope is to the tangent slope. So you might think, here's a great idea. What if we just set delta x to 0? Let's try that. So here's the slope of the secant line right here. It's f of c plus delta x minus f of c over delta x, whether you use delta x 1 or 2. Let's try this. You want that tangent slope, so let's set delta x to 0. What would happen? Because the implication here is when delta x equals 0, your secant slope becomes your tangent slope. And that's actually somewhat true. Well, let's go to the formula for the slope of our secant line, and let's watch it become the slope of our tangent line. So m tangent should be equal to m secant when delta x is made small enough. In fact, make it very small, make it 0. Watch what happens, though. We have a little problem. So it's f of c plus delta x, which we've set to 0, minus the f of c, all over delta x, which is 0. And I think you can see that this isn't going to work. It was a great idea, but look at what we ended up with. This ugly thing. Now, we refer to that as the indeterminate form. And the reason it's indeterminate, it's even worse than just plain dividing by 0. If you divide by 0, I think usually the implication is that the curve is going off to infinity. But the problem is, this is just completely undefined. Here's why. Division by 0 usually implies infinity, plus or minus infinity. But 0 on the top of a fraction usually implies that the value is 0, actually. But same over same usually implies 1. So which is it? It's just undefined. Completely undefined. And the reality is that's not working because the tangent slope is not undefined. It's right here. I can see it with my eyes, but I just can't acquire it yet. So that's not going to work. You can't just set delta x equal to 0. So we need a process through which we send delta x to 0, but we don't actually touch 0. If we touch 0, the slope all of a sudden disappears right where you want the answer. So what do you really want? You want delta x to be infinitesimally small, but not 0. And how do we do that? Well, we need a new form of mathematics to do that. In fact, we have such a form of mathematics. It's called a limit. And we use LIM to represent a limit. And in fact, we send delta x to 0. This is called a limit. And it takes delta x and it sends it off to 0. But in reality, it gets as close as possible to 0, but in a sense doesn't become 0, because right where you become 0 is where the tangent slope. So it becomes 0.000000000, as many zeros as you can imagine, maybe a 1 at the end. And even your number, there's something smaller than that because I can inject more zeros. So it's the smallest number that is conceived. But basically what this says is, can you tell me the answer anyway? I know that if I put delta x equals 0, it fails, but what would it have told me if it worked? So you really want the tangent slope? The tangent slope is not quite equal to the secant slope. It's equal to the secant slope with the limit process in play, where delta x is being pushed to 0 but never quite reaches 0. So that's how we translate a secant slope into a tangent slope. So we're going to have to learn about limits in order to do that, and that's in another video. And the very last thing I want to talk about is the area beneath a curve. We'll finish with that. So take a look at the area beneath a curve. Now, if I were to give you a curve like this, f of x, and I said to you, could you give me the exact and precise area entrapped by the curve, x equals a, x equals b, and the x-axis itself? You could shade it in. There's very clearly some kind of area in here, but measuring it and calculating it is awfully difficult. So you could try to break it up into different geometrical figures that you recognize. You maybe put a big rectangle in there and maybe a few triangles on top, but those are going to be estimates. One of the things that we do, we can do this in calculus, but one way to get there is to do just what I mentioned, and that is use some familiar geometric constructs, like rectangles. Let's draw a couple of rectangles in here using points from the curve, but making them flat. Making them nice and flat. So instead of getting the true area under the curve, we're going to get the area of these rectangles. We'll get area of rectangle 1. We'll add that to the area of rectangle 2. We'll add that to the area of rectangle 3, which looks pretty accurate actually. And then finally we'll add the area of rectangle 4. But notice that it misses a piece here. So I've got to say this. The area underneath this curve is not equal to, but approximately equal to the sum of these 4 rectangular areas. That's pretty much the best I can do for now. This will be A1, A2, A3, and A4. So I'm trying to fall back on something I do know about, and that's the area of a rectangle. Is it the exact area under the curve? I think you can clearly see that it is not. I've got some overshoot and I've got some undershoot, and I'm not sure that the overshoot and undershoot are exactly going to meet. Sometimes we have more overshoot, sometimes we have more undershoot. Is it close? I'm sure it's pretty darn close. We need another form of mathematics in order to get that to be exact. So we're going to discuss limits. We're going to discuss the tangent line and other ways of determining things like the area under a curve as we get a little deeper into it. So tune in to the next video, and I will see you shortly.